Hello, Sauce here. This is a lesson on instantaneous rate of change from what we know about average rate of change. This is a lesson in a series. The previous was average rate of change as velocity. Let's talk about that a little bit. Imagine being in a car traveling 120 miles in 2 hours. We can easily calculate that the speed of the car must have averaged 60 miles per hour. That's a change in distance of 120 divided by a change in time of 2 gets your rate of change of distance 60 miles per hour on average. Now the car might have gone 60 miles per hour at least once during that trip, but it doesn't go 60 miles per hour at all times during that 2-hour interval. We find averages meaningful, but the most common experience of being in a car is looking at the speedometer and reading how fast the car is going in an instant of time, not on average during an interval of time. So let's approach that idea on paper by reminding ourselves what we mean by average rate of change from a graph, and then extending that to the calculation and the expression for average rate of change that we can do with algebra. On a graph, I'm going to draw a generic curve. And on this curve, we're going to have a starting point, and we're going to label it in general terms with an x. This could be any value x. And after a certain amount of change, we can arrive at a second point, and we'll label this point x plus the amount of change from when we started. Now, if we're going to express the coordinates of these points, then we'll need a function to find the values given these two locations in the domain. We can most generally call that function f, and then express the value of the function at x as f of x. The value of the function at this later time would then be f of x plus h. This change in the horizontal variable I've chosen to represent with a single variable we're calling h. The average rate of change then between these 2 points, we've talked about in the past, is the slope of the secant line that joins those 2 points together. And we want to remind ourselves that what we mean by a secant line is one that intersects at 2 points. Again, the average rate of change is the slope of that secant line between those 2 points. And we calculate a slope as a rise over a run. It would be the vertical change divided by the horizontal change. And because we have ways of labeling that change symbolically, then we have an expression for the average rate of change. Or we could abbreviate this AROC. The expression for the average rate of change is a rise over a run, but we're going to use the function notation for the rise. It's the latter vertical value minus the former vertical value, or f of x plus h minus f of x. And then we'll divide by the horizontal change, which we've labeled as h, making that the simplest possible way to express that slope. So where do we get instantaneous rate of change? Well, in this presentation, we have, of course, 2 points, and the horizontal distance between those 2 points is h. The h is a variable, so we can imagine reducing h. H can get less than what we've presented here. Visually, graphically, that means that the distance between these 2 points could shrink. They could get closer together. I could imagine an average rate of change by moving this point closer to my starting x value. It would still be the slope of a secant line if these 2 points are separated by any distance h. But what if I exaggerated that and moved this second point all the way to the location of my starting point at x? If we slide this second point so that it is on top of x, we no longer have a secant line because there's no 2 different points to draw a line between. I can still draw a line. It would intersect just that 1 point. And if it intersects 1 point, it's not called a secant line. We have another name for it. It becomes what we call a tangent line. A tangent line is one that intersects at 1 point. But what did that do to the expression to calculate the average rate of change? Well, the expression, something happened. We still have a vertical change that can be calculated f of x plus h minus f of x. What changed in the expression is the distance between these 2 points. The distance between the 2 points, when we got the second point and slid it closer and closer to x so that the distance between them disappeared because the 2 points became to be in the same location, means that the distance became 0. But what happens if we replace 0 or replace h with a 0 in this expression? We would then be dividing by 0, and we can't do that. So we need help from calculus. We need that distance to be approached as a limit. If I put a limit statement in front of the average rate of change expression, then I can think of what's happening to the rate of change as the distance between the 2 points goes to 0. And if we think of this horizontal variable often representing time in contextual problems, then that value for h is a measure of time. And what's happening when h goes to 0 is time, or the interval of time between the 2 measurements, is going to 0. And when we have a measurement taken in 0 time, we call that an instantaneous measurement or an instantaneous observation. If this interval, h, goes to 0, we're no longer calculating average. This expression, which includes the limit, then is what we call an instantaneous rate of change. And we can abbreviate it with IROC, the I being for instantaneous instead of the A for average.